Hey all, good afternoon. We'll start. So I'm going to talk about approach for some impact analysis we have done of the flash behavior, the NAND flash behavior on the QoS for the DC and enterprise SSDs. All right. So if any question and queries in between you can ask, or at the end of the session we'll have some Q&A. Actually, my name is Ravi Shankar Singh. I'm from Samsung Semiconductor, India. My partner who contributed to the experiments, Yogesh Khurana, unfortunately he didn't make up here. So I'm going to cover all the presentations. This is the agenda for today's presentation. First is introduction, we'll cover. Then some basics about the NAND, SSD architecture, and some IO operations, garbage GC, OP, over provisioning. And then we'll move to QoS in detail. So QoS parameters, how the matrices impact. And then NAND parameters and software policies of the NAND, how it's going to impact the QoS. All right. And in the end, we'll see some results. So these results are based on our experiments of the various products. Okay. So if we talk about the performance, whenever any vendor, they release any SSD product, so normally they give the specifications, and performance is one of the highest rated feature of the specifications. All right. SSD performance is always evolving. The reason is NAND speed as well as host interface speed is always going to increase by generations, right? So let's say SATA or SCSI or NVMe. So every 2 years, these speeds are going to be changed. So NAND has to make the speed upgrade with that speed to make the QoS and performance upgraded. But the real problem is the quality of service. Okay, so even though our NAND speed or host speeds going to increase, but there are few things which going to always be challenged for the QoS. Okay, we'll see in upcoming slides. Coming to the NAND basics, so NAND has some intrinsic properties, right? So any erase operations which happens always in the block unit, right? So NAND is always divided into the your chip, die, plane, block, pages, right? To make it more interleaving and parallelism, right? So basic erase operation is always supported by block units, while program and erase are supported by the page unit. So if you see, this is the matrix, how the strings is operated, right? So string of the NAND, right? So this divided into word line and bit lines, right? So these are the NAND cells, and these word lines actually they defines to the page, and finally the whole these word lines define to the one block, right? So this is just a basics for in this one to understand that how the cells are divided and how the page and blocks are formed. Now going ahead with the NAND basics, NAND is always divided into the SLC, MLC, and TLCs. So as I told, like word line forms the pages, right? But if it is SLC block, there will be only one page formed, okay? And program and read operation which happens in the page level only, right? But erase, if you see, erase happens at the block level, right? So to erase the data from this page, we have to move the data from this page to other blocks, free blocks, and we have to perform the garbage collection. So that's why the erase is for the full blocks, right? So SLC block will only form the one page for this word line, while the MLC block will have the two pages. TLC block will have three pages like that. QLC will be the four pages. So till QLC, the current generation NANDs are. So coming to SSD architecture, SSD, this is overall picture of the SSD geometry. Okay. So as I told, the device is parallelism and interleaving, the two key feature of SSD. All right. So if you see the host interface, there is divided embedded processor with the device head, and the hardware channels are there, right, to achieve parallelism. And these NAND flashes, these are the array of flashes where each channel operates. And these are the packaging where, so this we can say the chip will divide into the dies, and dies go into the plane, then plane will form the block, and block into the pages. So these are all the parallel operations. So if the IOs outstanding, any IOs comes or in command comes, it will be divided into these channels, and finally these divided into different chips and the dies and block and like that. So we'll see how this is going to cause an issue because this is very important feature of the SSD to improve the performance. But this is going to, some cases is going to cause the bottleneck, right? So some SSD IO operations, as I told, like these are the host interface, the SATA, SCSI, or PCIe and VME. So this speed is going to increase. NAND in speed, this interface is going to increase. So the real thing comes here, how to maintain the performance, right? So this is a very basics write operation, okay? So if SSD controller you take, so these are the two cores, host interface and NAND interface, okay? And in between the software is running as FTL. I mean, I'm talking about some particular device. These cores may increase, may change. So based on the vendor, some vendor make this controller the 3 cores, 4 cores also to manage. As you go, the NAND density increases, NAND speed increases, you need more cores to handle this, right? So this is the write flow, right? Data goes to the cache, and then flush will happen. And in between, if there is a bottleneck, the GC will be triggered, and finally your data will be, DMA will take care of the write operations. This is the read flow. Okay, again the same, the host interface, NAND interface, read will go, and it will try to do the NAND read. Okay, so FTL has a 80% role where your address translation happens, because host will give you the LBS and this will be translated into the NAND LPNs, right? So NAND read, it will try to read from this NAND. If it will fail, it will do the couple of retries. And here the NAND, the read operation actually goes for toss, okay? And if it will get the data, it will go for the status. So till now we have seen the NAND Basics and SSD geometry architectures, okay? And it is going to impact our QoS, okay? So we'll see how. So now come to the firmware policies. So garbage collections, as I told you earlier. So this is a block. So always erase operation will be performed the block level, block unit, right? So in a block, whatever the pages are there, we have to move into some free block or good block, okay? And then we have to make it free, the third one, okay? So how it is done is identify which page contain the stale data, which we have to move it, move the pages from good data to another block, and erase the original block, right? GC is very common feature of SSDs, or if you talk about the memory storage domain, but it has great impact if you see here. So first impact will be on PE cycle, okay? So as you know, every SSD or flash comes with some lifetime, which is measured by the program erase cycle. Okay. So GC will be performed to maintain the P cycle. So one of the reasons is there. It has the impact on the endurance because your sales P cycle and your leveling has to be managed. Okay. So that's why GC is very important in that case. And to reduce the performance, particularly in the case of wherever the sequential IOs we are going to do. If let's say sequential LBAs you are not going to get, you have to do the GC operations to get it. So GC is very important and it has to be managed well in the policy side. All right. Next one is over provisioning. OP, if you talk about, so every vendor or every SSD has some fixed NAND sizes, okay? But we don't know. I mean, user doesn't know what is the NAND size. NANDs are there in the SSDs. But user capacity has to be determined based on the IDMS standards, okay? So this is a disk equipment material association which defines what will be the LBA size for any disk. Okay. So let's say we have the 1 TB of drive. So the maximum LBA has to be defined based on these standards. Okay. So NAND, whatever the NAND you have, that doesn't matter. What is this and IDMS standard defines, that matters. Okay. Based on this, the OP will be decided. So this is a formula where the OP, this percentage of OP is calculated. So why I'm talking about the OP is OP actually decide a lot of things here. Yeah, please.
Your definition of OP is different from industry standard. Industry standard is NAND, physical size minus user size over user size. Is that a typo or is that how you define it?
Yeah.
Is that typo?
Yeah,
It's physical minus user over user.
okay, you were talking about this physical, right?
Yeah.
Yeah, I think it's typo. Yeah, typo. Yeah.
Denominator should be user, right?
Yeah. IDM is user side. User.
The denominator divided.
Yeah.
Does that mean?
So this will be the user side. Yeah. Thank you. High OP. It means you have the more NAND, all right, and more NAND will always go for the low GC. Your GC will be low, and right amplification factor. Since you have the more NAND, low GC will be there, so your right amplification will be the low. And this cause finally the performance will be good performance will get in this case. Okay. So this is the impact of the over provisioning. So till now in generic we covered basics of NAND, SSDs, firmware policies, right? Now come to the quality of service. So what is QoS? QoS is quality level STD and consistent performance of all the requested processes. So all the process must finish in certain specific time limit or certain target confidence values. Okay. So all the processes, when any outstanding IOs are there, it has to finish under certain time limits. So that is the basic of the quality of service. Now it talks about the storage, talks about the networking. So I mean basic definition remains the same. Okay. But in case of storage, this is a challenge. The reason is SSD policies and characteristics interface into the IO completions, right? So let's say even though we have the good interface speed, okay, we have the good NAND speed, but if you have the poor SSD policies, right, what happens? Your completion and latency will be on toss, right? So if you see this graph, the right latency, this is my target acceptable performance level, but because of some GC in between and we are leveling, right? These are the outliers. And these are the outliers which is causing my QoS drop. And we've seen there are a lot of customer comes with these questions. Okay, so this is the typical scenario in current industry where these outliers cause the problem for the SSD vendors. QoS parameters, how we measure the QoS. So normally workload access is important. Read, write, mix, stream. Queue depth is important because whatever the device side QD, what the spec says, that has to be matched. Or I mean up to the match. Let's say 32 for the SATA, that's easy to match, but the problem with the NVMe 64K queue it supports, but normally it's very difficult for the firmware to maintain this 64K. Okay. So yeah, so queue depth is important in this case. So whenever you are generating the workload with FIO and all, so 64K with the it will cause a lot of bottleneck the device side if you give. So we have to know the queue depth of the device policy. Block size definitely 128 KB sequential and 4 KB random the device we consider. And device state, this one lasts, but it's very important. If the device is clean, your performance or QoS is definitely it's very good. But it goes in the sustained state, it will be challenged, right? Because you don't know what the policies is being triggered if it is sustained state. So there will be the outliers in this case. So all the maximum outliers fall in this categories when the device is sustained state. QoS Matrix, if you talk about, if you see the SSD specifications, they will talk about the latency, average, and nines, 2, 3, or 4 nines maximum the specifications. But they don't talk about the higher nines. So higher nines comes when the industry they measure. Okay, so 5 nines, 6 to till 9 nines. So here is the problem. To match these higher nines is a great challenge for SSD vendors. Till a specification, this side is fine. We'll meet all the values, but higher nines is tough. Consistency value is 95% or more. That is a requirement for the QoS. Factors for the QoS behavior, we can see. So host factor and device factor, we'll ignore the host factor for this session. We all know CPU mode, schedulers, RAM speed, the protocol interface. So let's assume host factors are fine. We'll cover the device factors because our session is based on this. So NAND parameters, NAND timings, NAND interface speed, NAND geometry, OP, PLP, power loss protection, program erase, suspend and resume, and garbage collection. So these are basically first NAND parameter is intrinsic to the NAND. We can't do anything. These are the related to software. We can play a trick here. Okay. NAND parameters, if you talk about, there are a lot of timing parameters you can see. So SSD vendors talk about a lot of timing parameters, but in this case, we'll take care of these 3 parts. TR, which is a page read time, tPROG, which is page program time, which is SLC, TLC, MLC, block erase time. Okay, so these are the 3 timing parameters in the specification also we mentioned, and these are the main parameters which plays the role in the QoS performance. So better TR, PROG, and block erase means there are good timing and there is improved latency. Okay, but TR and tPROG has the impact on the program and erase, suspend and resume latency also. Okay, so we'll see that in the coming slide how it impacts the program erase and resume. NAND geometry. If you have the better geometry, you will have the high interleaving, right? High interleaving means you will process more commands. So parallelism will be good in this case. So obviously QoS latency will be good. Obviously software policies has to be supported in this case. If the geometry increases, your complexity of software will increase. Better NAND interface means improved latency. So this is very straightforward. If there is a NAND interface speed is high, your latency will be good. PLP has impact on the performance, particularly on the QoS side. First of all, what is PLP? Power loss protection in SSD. It safeguards SSD in case of power loss. Okay, so if you see the SSD vendors, normally they provide with some capacitor in case if there is a power failure, the capacitor will sustain for some time. It will provide the power so that your metadata will be synced, and it will safeguard your SSD. Okay. So in case of power failure, PLP helps to flush transit data actually. So normally when there is a power failure, PLP will flush the data to the NAND. Okay. But the problem is it will turn off your cache. Okay. So when the cache will be turned off, so definitely the performance degradation. Okay. So whatever the outstanding IOs, that will directly go to the NAND. So if there is a reliable write to the NAND, your performance QoS will be compromised. Okay. So PLP has this side effect. Okay. Provisioning thing, we have already talked about this. Okay. One point I want to make it, OP has an impact on WAF, write amplification factor. Okay. So if there is a read intensive SSDs, there are normally this shows a 10% OP, and there are high write amplification factor. If there is a mixed pattern SSD, so these are the 30% with the higher side of over provisioning. Okay, and since OP is high, your WAF value will be low. Okay, I can't see. Okay, this was I was talking about suspend and resume operation. So in SSD software, read has the highest priority in terms of IOs. Okay, so read IOs has the higher priority than program and erase. Program erase suspend if it interrupts with the read IO. So if let's say there is a program or erase operation is going on and there is a read IO coming, right? So it will suspend. Okay, but this suspension will have some impact. Okay. So high IO latency because of this suspend and resume operation. So suspend will come, then again it has to wait, and based on the priority or timeline, again it will resume that operations. So based on this suspend and resume operation, your performance or QoS will be slow. So this you can see the picture is not clear, but erase, it should be smooth like this on one graph. And because of the read operation, it is just in some wave. Okay. So this is suspend, resume, suspend, resume, suspend. Instead of only it is going the smooth, it is going suspend, resume, and it has the overhead, which will cause the low QoS. So this is one of the things which will be always controlled by software policies. So here IO operations are delayed because of the time of suspend resume and time of resume suspend latencies. So these two timings are extra apart from your NAND parameters, right? So these two timings you have to control it. This is the few results I want to talk about. We have taken some SSDs of the older generation versus newer generations. Okay. And we have seen some parameter changes. Based on the parameter changes, how these QoS have changed. So in one of the case, there is a TR drop of 10%. Okay, so TR timing drop 10%. So read was the highest drop in this case. Obviously, the reason is the NAND read operation is very slow in this case. So read QoS is slow. Write also dropped in this case by 12%, and mixed read write is 20%. Okay. In another scenario, we have taken the geometry change where die size, one of the older product which is having the die of 256 GB to, okay, now the latest product is having the one die of 512 GB, okay, NAND. So because of this die, now from 2 die to you made it to 1 die, so interleaving and parallelism is reduced, and you can see the very drastic change here. So read is highly impacted, which is there are a lot of questions from customer for this, around 44% null. And write QoS and mixed QoS, again, I mean, this is too much drop actually. So this is, we can say has the highest impact if there is a geometry change. NAND type, if you change it from the MLC to TLC, from 2-bit to 3-bit, your read QoS dropped, but the change is in the write and the mixed QoS. The reason is bit density improves the program latency. So bit density here was 2-bit, and here it is 3 bits. So if you are writing the data, you are writing in the highest bit density, and the write QoS is improving, but the read QoS is a problem in this case. Yeah. And these results are all relative. So the absolute values we can't publish here. So these are the references. Thank you. So any question for me? That's it. Yeah, please. So IO pattern here is 100% read, 4 KB, okay, and yeah, so this is around 99 percentile, yeah, and similarly in the write QoS too, it's 100% write, 4 KB, and 99 percentile, and here it is we have taken around 50%. Yeah, please. You mean to tell this? This is drop from the old product to new product, actually. So older product, let's say, I mean, product to product changes. One product has some X, so other product has a 10% increase in the TR time. So in that case, there is a changes. So this comparison between the two products generations. Any more questions? Sorry? Performance or time? These are the performance latencies. Yeah. So these latencies normally comes in the microseconds. Yeah. Absolute value is microsecond, but this we have taken in the relative value. Pardon? Slide number? 18. Yeah? 9. This one? This one? Yeah.
I was curious about the rate-intensive workload having a higher rate application.
Okay. This is the data we have taken from one of our SSDs. Okay. So based on the customer requirements, so read operations normally doesn't cause much of the GC operations, right? So that's why they want to keep it the OP percent over positioning low. And the other impact is they want to keep it the high write amplification factors. Okay. So read, that's why the read intensive application has a low GC, so they wanted to keep it as the OP as a 10%. Well, the mix pattern SSDs around, they're keeping 30% more because write cause the GC high, right? High GC cause to compensate this 30%, yeah. Yep.
Do vendors make it difficult to find out the product, the RLS protection features of SSDs? I guess this is more on the consumer side than the enterprise side.
Yeah, so
It seems like a fundamental thing to, you want to be selling reliability. I understand this performance trade-offs.
exactly, yeah,
Yeah, it's a weird product.
right.
You can hide unreliability.
If we talk about the client, if you
Well, every few years something comes out with a test where you actually test a bunch of recipes to an automated switch. And you run a workload on them and you flip the power every once in a while. And I think the last one I saw this past year was all but 2 grams of SSDs failed. Relatively quickly. What does fail mean? The device stops responding or the device is no longer reliable. So
That's a different issue.
Appliance got a different approach to it.
I would hope my company don't fail that.
Right. So my question, my original question is that was it hard to discover which ones actually take care of that kind of thing? In this case, the person refused to mention the two things that
All you would ever see on that is market fees. So it's hard to get that.
okay, PLP, sorry,
I was just going to add to that.
yeah, okay,
This is not vendor specific at all.
right.
PLP capacitors are expensive. And so you have really commodity drives, people are trying to get the biggest capacity for the lowest cost.
Right.
What's a corner you can cut? PLP protection. And it's not even that bad for some applications. We can have something like a notebook, which necessarily has batteries, so that both the chance of being drive losing power without any ability to save its contents is fairly low. But it's basically a price point
Right, correct.
consideration.
Thanks, Rory. So that's the point actually. If you see the client or brand products in SSD, so normally which we use for the boot drive or normal laptop drives, these are the, as Rory mentioned, the price is a thing which has to be considered. So client and brand products normally they don't keep this feature because of the high cost. If you go to the enterprise and DC where reliability is very important, right? In that case, definitely PLPs has to be kept. So that's why the cost is higher side.
Sorry, but that's a system design in a lot of
All right.
It's not a device design issue. And most system makers are cognizant and work with their preferred suppliers to make solutions work. just build it yourself, like myself.
Any more questions, please? Yep.
You mentioned that the host parameters like IOS delivered were kept constant. But given a factor, if you were to compare scaling algorithms, which are
Right.
different now and there are some new ones like hybrid and others coming in, have you done some analysis of which scheduler works better in certain workloads versus others?
For these experiments and our test parameters, we are using NOOP. We are just bypassing. We don't using any customized schedulers in this case. Yeah, definitely your question. There are a lot of studies in terms of the scheduler parameters where the benchmarking has been done based on the scheduler. But in this scenario, we have only used the NOOPs.
One thing I'm confused with is I'm not sure. So are you recommending here a new way of actually looking at costs for your drive, or for ATA is pretty much what standard how anybody in the industry measures cost? So trying to understand like when we are evaluating drives, or let's say when you're proposing a new way or new parameters which your customer should be looking at.
No. These are the relative study where we have done different records of product. So some products, these are the changes across the generation of products, right? So these are the study we have made that the like newer products which we are having the die size of 512 GB, only one die instead of the two dies up to 56 GB. So this is going to impact on this scenario. So in coming to your question, answer is yeah. We have to think about these parameters when you are defining the new SSDs, okay? But in current scenario, this particular session or result is comparison between two drives. More? Thank you.